Okay. All right. So we've got this circuit example here. The first thing we want to do is figure out what is the logic function. And we can get the logic function. I just go ahead, you guys figure it out. Take a minute, figure it out, and then I'll tell you what it is. I'll give you a little bit of time to make this thing work. Okay. Okay. This is what I get. That's what I got. I used to make people do this in class and take these up for points. It was a make work thing for the graders. So what I've got here is I have the parallel combination of A and B is in series with C. So I'm going to put the parallel combination is going to give me an OR. And I have to put that whole parallel combination in series with C, which is an and then put a bar over the whole thing. Over on the PMOS, I want to double check that to make sure it works. A and B in series is now an A or B, and that right there is in parallel with C, and then I knot it. Now, we could look at this from a transistor viewpoint too. If we're not too sure and we want to figure out what's going on with the function. We could go back to our little on-off model of the transistor. I've got a particular state here. So A is high, so I'm going to put a 1 on A in both places. B is low, so I'm going to put a 0 on B in both places. And C is high, so I put a 1, and I put a 1 here. The NMOS transistors that have highs on their gate are going to be on. And the ones that have lows on their gate are going to be off. The PMOS transistors that have highs on their gate are off. And the PMOS transistors that have lows on their gate are on. Now, what I'm looking for to figure out if it's high or low is I'm looking for a low resistance path to ground or VDD through on transistors. So looking here from Y, I've got a low resistance path through C, and I have a high resistance path through B, but I can bypass that and go through transistor A. So my output is going to be low. And I want to double check, make sure I don't have a low resistance path on the PMOS. And on the PMOS, if I got an on transistor here, but I get blocked by that off transistor. If I try going through this path, I'm going to be blocked by another off transistor. The beautiful thing about this is very little current will flow in CMOS when I'm not switching it. If I'm in a static condition, I always have a high resistance between VDD and ground. So not much current flowing, not much power consumption I can stack these transistors into a really small space without melting my silicon, in theory. When you get into the new Intel processor, and a lot of the new processors, basically, they have this phenomenon called dark silicon. If you turned on all the parts of this processor at the same time and had them running in parallel, you would generate enough heat to melt the chip and permanently destroy it. So they actually have a little microcontroller off on the side of there, which is telling you that, oh, you can only run this chip at 70%. So when I'm doing a computation in the ALU, I'm going to have to shut down or put the memory into sleep mode. I'm going to have to put different parts of the processor into sleep mode dynamically to keep the power consumption down. You can fix that by lowering VDD even more, but that requires some more processing hijinks. We'll talk about that in 380. Okay, so I get a more complicated circuit. So go ahead and take a minute and try to figure out what this logic function is. This is not a standard gate. And my technology's behaving today. I have the series combination of C and D in parallel with B, and that whole thing is in series with A. And then I put a bar over the top. And if I check the top function, I've got C and D in parallel in the PMOS, which is an AND. That's in series with B, so that's an OR, and that whole thing is in parallel with A. So looks right. I think you get to do this on the homework too. A is high. Yeah.
So I was telling them the PMOS ones are easier to see when you go to drive your Boolean expression.
Okay.
It's like, yeah, your E and D or whatever, they're parallel. So
They're right next to each other, so it kind of looks like an AND.
So the expressions are easier to see that way. In PMOS, yeah.
For me, it's exactly the opposite. I always go for the NMOS first because I think if they're in parallel, it's an OR, because that just kind of like I can go one way or I can go the other way. But whichever one's easier for you, do that one first. And then check it with the other one. Okay, that's usually helpful. If you have something to double, you've got something on the diagram to double check your work, so you're probably okay. So we're going to make A high, 2 transistors. We're going to make B high. B is high. C is high. And D is low. So I've got this transistor's on, this transistor's on, this transistor's on, and this one's off. And I already see my path right here. It's going through this way. A lot of time it's harder flipping. The way I design these, I draw the NMOS network first because it makes more sense to me. And then I take the NMOS network and I say, okay, these are in series, they now have to be in parallel. And then these are in parallel, they now have to be in series. But if it's a function like this, I sometimes have trouble getting that, oh wait, this was in series, do I and it's in parallel up here, Do I stack this B on the side of it, or do I put B on top of it? I get a little bit mixed up there. So it's always good to kind of like double check your function, especially when you're first learning how to do this. I've been doing this for 9 years. I actually probably longer than that. I actually worked and I did this. Or no, I watched I watched Bruce Hancock do it. We had to, when we were building our imagers, they came up with the idea of let's build photodiodes in the substrate. And at the time, nobody was building photodiodes in the substrate. So the people who were actually doing the processing and making our integrated circuits, we were able to get it past them. We're going to violate your design rules. And we're going to just do this little thing right here, putting diodes in the substrate. And they'd say, okay, we're fine with that. I mean, there's like 2 or 3 manufacturers we could get to agree to that. And then the next thing was that we have to go out, the next logical thing would be, is to go out and buy a standard cell library from someone like Xilinx or HP, who's already built a whole family of flip-flops and AND gates and inverters and NAND gates that we can use to do our microcontroller design. Every single person looked at this that we went out to and said, no, you're violating the design rules. We're not going to get blamed when this doesn't work. And we're not putting the photodiodes underneath the microprocessor. No, no one would sell us their IP for this. So we had this PhD from Caltech, and part of his job was to build us our own standard cell library. And I kind of helped him out a little bit. And then I took his standard cells and built a processor out of them. But we had to do the whole circuit design from scratch, including building our own flip-flops. I could handle things like 2-input AND gates, but when it came to doing flip-flops, it was Bruce just, he'd hold himself up in his office for about a week and come out with a flip-flop. And we'd all look at it and we look at the simulations and we'd nod and go, very good. So we're going to check on the top too, make sure it is actually off. So I don't have this is an off transistor. This is off. This is on, and this is off. So the only path I have through an on transistor is right here, and it dead ends. So this whole network is off. This one's on. It's going to pull it to ground. My output will be low. Okay. So this is one problem I could give you on the exam on these NMOS or standard CMOS circuits. I could give you a circuit, I could ask you what the function is, and I could ask you to analyze it. Now this is another way I could do it. That's what I did in 380 this semester. I could give you an NMOS network and ask you to draw the PMOS network. So the first thing I want to do is I want to write down the logic function. So I've got A or B, they're in parallel, and that parallel combination is in series with both C and D. And then I remember to put the bar on the top. Okay, now I've got to flip this around. I've got D, I've got 3 things in series here. I've got D, C, and the parallel combination of A and B are in series. So I'm going to have 3 parallel networks. One of them is going to be D. One of them is going to be C. And the other one was the parallel combination of A and B. So now this has got to be the series combination of A and B. And one thing I'm kind of a stickler about if you're drawing these circuits is that this top has got to be tied to VDD or it won't work. And this bottom has got to be tied to ground or it won't work. Yeah, I just take a point off. But I do check that. Things don't work without the power and ground connection. A few more slides yet. Oh, two more. We're almost done. We want to draw the static function. We're given a function. We want to draw the whole circuit. So this one has the bar on the top. So I don't have to worry about putting an inverter at the end. I've got three things and I got a three input and I've got a 2 input and. Now for NMOS, the and is series. So I'm going to need 3 transistors in series. It's like I do this all day long. I'm going to need 2 transistors in series here. And this one will be going to A, B, C. And then I have D, and I have E. And that's the end of my PMOS network, and that is Y. Now I've got to flip that around, and I'm sorry, that's the NMOS network. I may have said PMOS. I've got to flip that around and draw the PMOS network. So the PMOS, what's in series becomes parallel. So I have a parallel combination of 3 transistors. And that is A, B, and C. And that has to be in series with another parallel combination. So I'm just going to draw a little line across that and make another parallel combination that's running out of room in series with that. So that would be D and E. Pretty much any function I have, I can build a custom standard CMOS. The way we did it when we built our library is we built an inverter. We built a 2 input NAND gate and went all the way up to a 10 input AND gate because that was the biggest AND gate or NAND gate. That was the biggest NAND gate we could do and still meet our current specifications for having the correct power out and having the drive capabilities. And then we built 2 input to 10 input NOR gates. Now, because we are not really worried about space efficiency, we're worried about the time efficiency. If I wanted to build an AND gate, I took that NAND gate and I put an inverter on the end of it and made a cell called AND that if you look down, it was a NAND and an invert. And then that went down into the standard cells. Okay, so how can I possibly make this worse? And this is about it. Let's draw the static CMOS for A, B, C, or D, E without the bar. Now, the quick and sloppy way to do this, and I've seen people do this, is I just put an inverter on the end of this. So I could take my old schematic, I'm trying to erase it with my finger like it's on the whiteboard. I could take my old schematic and just add in an inverter. So I would need an NMOS. Wait. I need to get rid of that wire. I would build an NMOS inverter, build a PMOS transistor, and this would be my new Y. But when I do that, I now have 12 transistors. If I want to fit this into a small space, I've got a memory array and I've got maybe 9 nanometers to fit the whole wide to fit the whole circuit in. And they want me to keep it as short as I possibly can. Having those 2 extra transistors are going to cost me a lot of space. So there's a little trick I can do here with De Morgan's theorem. And if you've had me for 110, you've probably heard me say a few times, De Morgan's theorem is the only theorem in algebra I care about. This is why. how I do this. I'm going to take my A, B, C, or D, E, and I'm going to put one bar over it, and I'm going to put a second bar over it. I've inverted it twice. It's the same function. Now I'm going to apply De Morgan's theorem to it. And the part that I'm going to break up with De Morgan's theorem is this inner bar. I want to leave that whole bar, that upper bar over the top. So the first thing I do is I break this bar right here, and that becomes A, B, C naught times D, E naught. The shortcut, if you don't remember De Morgan's theorem, the shortcut version of that is I break the bar and change the sign. So I broke the bar right here, and I changed the plus into times. I'm going to break it again right here and right here. Since I'm breaking the bar, I will get A bar, B bar, C bar, and as I change the sign, the times becomes a plus. And that will be times D bar or E bar, and then I still have the bar over the whole top. That I can build with 10 transistors. I've saved myself 2 transistors. There are ways that we'll learn in like 380 that you can get rid of almost the entire PMOS network. There are ways to do logic. I can build an exclusive OR gate takes 8 transistors normally, but there's ways with past transistor logic you can do it with 2. Or you can do it, yeah, you can do it with 2. Now I want to draw this. I get a little bit different circuit. So the A or B or C is a parallel combination in NMOS. And I'll go over the objection I usually get to this. A bar. So I have to put A naught is what is being ORed. Not A, it's A naught. B naught, C naught. And then that is in series with the parallel combination of D naught and E naught. It's drawn a lot neater in my slide solutions. And this is Y. And then for the PMOS, I've got 2 things in parallel. I'm going to have 2 things in series. Drawing with a stylus on a slippery screen and I'm going to have this network down here will give me 3 things in parallel. What happened to all the math? So this will be D bar, E bar, and the position of D bar and E bar could be switched. It's not going to change the function. There's not exactly one right way to draw these. When I'm grading your papers, I just look at the function and see what it is. I figure out what your function is and see if it matches what I asked for. So we can build it with 10 transistors, 2 transistors less. Now you're probably thinking at this point, but I have to invert all those inputs. I have to have A naught, B naught, C naught, D naught, and E naught. And each one of those inversions is going to take 2 transistors. But in reality, most of these signals are coming off of a flip-flop. I have some register that's storing the information, driving the inputs of my static logic. And so if you look at a flip-flop, most normal flip-flops have both a Q and a Q bar output. The only thing this is going to change is which output I route it to. So I can actually save a few transistors like this. And we'll get into ways to solve, ways to save even more transistors in 380. And in semiconductor memories, generally what I do is I just throw up the circuits like the engineers built them, which are these weird hybrids of part of it's standard CMOS, part of it's pass transistor, part of it's dynamic. It's all just to be able to squeeze it into a small enough space and fit the performance requirements. And those weird circuits are generally used for things outside of the processor. Inside the processor, we stick to standard CMOS because it's reliable and it has the best performance. Are we going to talk about muxes? Do I have to talk about muxes today? How would I do? You want to do? Let's just go. Let me see if I can do a mux. We don't talk about muxes in this class, but if I wanted to get the function, what we could do here. Let me go to bamboo paper. If I wanted to get a mux, if I can write it as a truth table, I can actually create the circuit. So for a mux, let's say, okay, so on mux, I've got 2 inputs and I've got 3 inputs. So I've got A, B, and I've got select. Okay, and it looks like this. Select this A, and we'll call this B. And I want to design my mux, so, and then I've got my output, I'll call it Y. What I want to do here is, if select is 0, I'm going to have whatever's on A. I'm just going to call that A. My output Y will be whatever's on A. Well, this is easy. And if select is 1, my output is going to be whatever's on B. Select is 0. I want it to be, I can probably do this. If select is 1, this will be B. And if not select is 1, my output is going to be A. And what function that, and then I could draw the corresponding PMOS network. What I've got here is, if select is true, the answer will and B, or not select and A. I think that will get most of it, not. And then I would have to invert that. So you can, if you can write a truth table for it, you can pretty much build it with standard CMOS. That was a really good question. And I've never gotten that one before in like 12 times teaching this class. And this is the last slide here. And this is Dr. Brower's favorite cartoon. I just leave it in here because this is true. This is absolutely true. The amount of time that you put into this will determine whether you succeed or not. It's not how smart you are or how smart you think you are or how dumb you think you are or anything like that. If you take the time to practice doing these circuits, you can learn how to do this. And you just, what you want to do is what you practice. I happen not to like to practice programming, and that's why I'm not very good at it. Okay, yeah, I had a high school student, and it was, I somehow, I actually got a high school teaching job in February. So the other guy had to transfer schools, and he was taking the place of someone who'd been fired. So I walk into this class, second semester, Algebra 1, and there's this kid in there that has failed the first semester, but high schools just go ahead and put you in the second semester because they don't know what else to do with you. And he's failing in there again too. And about 2 or 3 weeks after I started, he just comes up to me and goes, I want to learn this. And I go, okay, you're free during my break period, so just come in here and work on it. And by the end of the semester, he passed the second part of Algebra 2 with a B. I mean, it was just this huge improvement of him sitting down and actually doing the work, and he could do it. And he thought he just didn't understand math. Just, you got to practice. Okay, that works with everything. So I'm done. We're getting out a little bit early for spring break, for St. Patty's Day. Stay away from the bars. You haven't been vaccinated yet. I don't want to see anybody get sick. But yeah, there will be no green beer there. There will be green beer at my next door neighbor's house. I can guarantee you they'll have a party. They're a bunch of students. Ibrahim, are you here? Abdul Rahman and Jordan Ramirez, you asked a question, didn't you? I'm just going to mark you because I think you answered it. Yeah. If I look in the chat, it'll be there. Oh, and Abdul Rahman's here too. Yes. I live in a student neighborhood. Stop. But it's a nice student neighborhood. Okay, I'll see you guys.